In Webb's first look at K2 to 18b, astronomers saw the fingerprints of carbon-bearing molecules, methane and carbon dioxide. Another expected molecule, ammonia, looked scarce. That particular combination matters. It suggests the planet may carry a hydrogen-rich atmosphere spread over a deep global ocean, a class some researchers call Hycean worlds. Picture a planet-wide sea capped by a sky of light gases, dim sunlight filtering down through clouds, pressure increasing with depth until the sea fades into a warm, high-pressure interior. If Hycean worlds are common, then the universe may be littered with deep oceans we've never known how to recognize. 99.7%. If a single number could rewrite our place in the cosmos, that would be it. Headlines say the James Webb Space Telescope has found a planet that's almost certainly alive. But numbers have stories, and stories have context. Tonight, we follow the light to see what Webb really found, why it's thrilling, why scientists are cautious, and why the truth is even more interesting than the hype. Look toward the constellation Leo, about 120 light-years from Earth. A small, cool star flickers in a steady rhythm. Every 33 days, a planet slides across its face and steals a crumb of starlight. That world is called K2 to 18b. Webb isn't simply a camera, it's a light reader. When K2 to 18b crosses its star, a tiny fraction of the star's glow passes through the planet's air before it reaches us. Molecules in that air absorb very specific colors, leaving barcode-like gaps. Read those gaps carefully, and you can name the gases, like reading an ingredients label you can't see. So where does 99.7% come from? It isn't the chance of life the way a weather app gives a chance of rain. It's a statistical label for a possible bump in the data, what scientists call a 3 sigma signal. Some teams see hints of a molecule called dimethyl sulfide, or a closely related cousin, in K2 to 18b's air. On Earth, dimethyl sulfide is mostly made by tiny ocean-dwelling organisms. That's why the idea is electrifying. But a 3 sigma hint is just that, a hint. Scientists need repeated, higher precision observations to be sure. Let's anchor the basics. K2 to 18b orbits a red dwarf star in Leo. It's about 2.5 times Earth's radius and more than 8 times Earth's mass. That likely means a thick, heavy atmosphere, nothing like the air you're breathing now. This is not Earth 2.0. It's a different kind of world, and that's the point. In a hydrogen-rich atmosphere, warmth doesn't depend only on distance from the star. The gas itself traps heat efficiently. Climate models for Hycean worlds allow conditions that are temperate to warm. If an ocean is present, it could be stable for very long timescales, long enough for chemistry to get ambitious. Here's why Webb's result matters even before we say the word life. Methane plus carbon dioxide, with little ammonia, tells us the chemistry isn't flat and featureless. Something is shaping the air. If an ocean really lies below, it would exchange gases with the sky, setting up cycles of carbon, hydrogen, and oxygen cycles that, on Earth, are entangled with biology. Life, if it exists, wouldn't have to be complex. Microbes do just fine. In fact, microbes are the greatest chemists our planet has ever produced. Now, about certainty. 99.7% sounds huge until you ask, certain about what? At 3 sigma, you're mostly saying the feature in the spectrum is unlikely to be a random wiggle. You're not saying what caused it, and you're not ruling out imposters. Could another molecule produce a similar signature? Could clouds, temperature layers, or unseen star spots trick the analysis? Could the models be biased by assumptions we barely notice? These are not gotchas. They are the questions that drive bold claims to either stand or fall. In science, extraordinary ideas earn trust by surviving careful attempts to break them. That's why you'll hear people talk about 5 sigma, a much tougher standard, before using the word discovery. So what might life look like on a Hycean world? Not cities under alien suns, not forests bending in hydrogen winds. If K2 to 18b is habitable, The likeliest residents are microscopic, tenacious chemistry machines that feed on gradients of energy and nutrients, dividing in the dark by the trillions. They don't need continents or shorelines. They need time and stability. A thick atmosphere, a calm star, and a global ocean provide both. That's the deeper reason some scientists dare to say such a world could be more habitable than Earth in some ways. More room for life's experiments, more time for those experiments to succeed. Caution is not the enemy of wonder. It's the guardrail that keeps wonder from running off the road. In the chapters ahead, we'll unpack exactly what Webb measured and why methane plus carbon dioxide is such a powerful clue. We'll trace the dimethyl sulfide debate, what the molecule is, why a tentative signal lit up the internet, and what it would take to turn maybe into we're sure. We'll meet skeptics who look for false positives before they look for fame, and engineers planning new observations to check the claim. If there's a real biological heartbeat inside this atmosphere, there are ways to hear it more clearly, and we're going to explore them. In the end, the first proof that we are not alone might not arrive as a radio call or a silver spacecraft. It may come as a pattern etched into starlight, a set of lines no geology can explain, a chemical rhythm that whispers, something is breathing here. K2 to 18b has given us a reason to listen carefully. Webb has given us the ears. Let's use them well. Call it the art of reading light. Long before we launched cameras to other worlds, astronomers learned that starlight carries hidden messages. Atoms leave fingerprints. Molecules hum, absorb, and glow in patterns as reliable as clockwork. James Webb is a master of this craft. It does not need to touch a planet to learn its chemistry. It only needs the planet to pass in front of its star and let a thread of light slip through its air before traveling on to us. Here is the simple picture. A planet transits its star. Most of the light reaches us unchanged, but a tiny slice filters through the planet's atmosphere on the way. Gases in that air steal particular colors and let others pass. When Webb breaks that beam into a spectrum, a rainbow stretched into thousands of fine lines, those stolen colors appear as dips. Each dip has a name: water, methane, carbon dioxide. The overall pattern speaks about temperature, pressure, clouds, and the thickness of the clouds. That story is subtle. Clouds can blur the lines, haze can flatten them, winds and day-night temperature swings can nudge the pattern in confusing ways. This is why the most important words in exoplanet science are not discovery and announcement, but calibration and repetition. Webb watches the same world multiple times, at different wavelengths, with different detectors, and teams compare notes. When the same features appear again and again, confidence grows. K2 to 18b sits at the crossroads of possibility. It is bigger than Earth but smaller than Neptune, a category our own solar system skipped. It circles a cool red dwarf in the constellation Leo. Its bulk suggests a thick, light atmosphere, the kind that can blanket a deep ocean without freezing it or boiling it away. Even before Webb, water vapor hints marked this world as intriguing. You will hear a new word in this story: Hycean. Astronomers coined it to describe planets with hydrogen-dominated skies over global oceans. Hydrogen is extremely light, so it puffs atmospheres into thick blankets that trap heat efficiently. On a Hycean world, the ocean does the heavy lifting of climate control. It absorbs, stores, and redistributes heat. It exchanges gases with the air above, setting the rules for what the spectrum should look like. Now bring in biosignatures. The word sounds like a magic stamp, but it really describes a chain of reasoning. First, you look for gases that are out of balance, molecules that should not coexist in those amounts unless something is actively producing them. On Earth, oxygen and methane are a classic pair. Oxygen destroys methane quickly, so seeing both together implies continuous replenishment. On a Hycean candidate, where free oxygen may be scarce, attention shifts to carbon-bearing gases and certain sulfur compounds that are hard to maintain without a steady source. That is why talk of an unusual sulfur molecule drew so much attention. If such a gas truly hangs in K2 to 18b's air, and if non-living chemistry cannot plausibly make it in those quantities, then biology would move from possible to plausible. But science earns its reputation by resisting excitement until the evidence is bulletproof. Spectral lines can overlap. Unknown photochemistry in a hydrogen sky can create imposters. The star itself can play tricks as its surface rotates and spots come and go. There is also the question of the star. Red dwarfs are efficient furnaces, but many are active when young. They flare and bathe nearby planets in high-energy radiation. Over billions of years, most settle down, but the early weather matters. Could a thin hydrogen atmosphere be stripped away? Could an ocean be sterilized? Models suggest that a sufficiently massive planet with a thick enough blanket of gas can ride out the storm, especially if it holds a magnetic field and if the star calms with age. That possibility keeps K2 to 18b on the short list of worlds worth watching. If you are picturing a blue marble with white clouds and green continents, set that image aside. A Hycean ocean would be dark, deep, and global, with no land to break the winds. The sky could be pale from hydrogen and hazy from photochemical smog. Yet beneath those clouds, stability might rule. Microbes do not need beaches. They need gradients of light, of chemicals, of temperature, places where energy can flow. Upwelling currents, thermal vents, and chemical mixing could all supply the gradients life craves. So how do hints become confidence? You look for patterns that are hard to fake, re-observe at the same wavelengths, and see if the features persist. Observe at new wavelengths where imposter molecules would fail and the real candidate would succeed. Watch the planet outside of transit, catching its faint thermal glow to estimate temperature and cloud cover. Stitch together a climate and chemistry picture and ask whether any non-biological model can maintain the observed mix of gases over long periods. There is a larger lesson here, beyond any single planet. Webb is teaching us how to do remote biology, how to infer metabolism without microscopes or landers. The logic is familiar. Doctors infer disease from blood chemistry. Ecologists infer forest health from the air above the canopy. We will infer life on distant worlds from their skies. The first time we do it beyond reasonable doubt, the universe will go from silent to inhabited in a single sentence. And if K2 to 18b turns out to be a bridge rather than a destination, if its most exciting signals fade under scrutiny, that will not be failure. It will be a map. It will tell us which paths lead to dead ends and which are worth following. The difference between almost certainly and certainly is where science lives. It is the space between thrill and truth, and we are crossing it one transit at a time. Start with the number that hooked the world, 120 degrees Fahrenheit. It sounds precise, even cozy, like a tropical afternoon, but planets are not thermostats with fixed settings. That number is a translation of something more abstract, the balance point, where a planet absorbs energy from its star and radiates it back to space. Astronomers call it the equilibrium temperature, and it ignores many real-world details: greenhouse gases, clouds, winds, and the fact that day and night split a world into very different regimes. If you hear exactly 120, remember that it is an average of an average. The actual air, if you could sail through it, would feel warmer in some places, cooler in others, and wildly different at different heights. Now look at the phrase, more habitable than Earth. What could that possibly mean? It doesn't mean better beaches or gentler storms. It points to a statistical idea. On Earth, life has survived for billions of years through ice ages, asteroid impacts, and continents ripping apart. But our habitable surface, the places where liquid water and gentle chemistry exist, is limited to a thin shell. If a Hycean world like K2 to 18b truly has a planet-spanning ocean and a thick, heat-trapping sky, then the volume of stable, liquid habitat could be enormous compared to our shallow seas. More volume and more stability over deep time could offer more chances for chemistry to stumble into metabolism and then refine it into something persistent. More habitable does not mean more pleasant for humans. it means more room for life to try. How do models turn starlight into climate? They start with the star's brightness and color, then add the planet's size and orbit. They include the known or suspected gases. Hydrogen is crucial because it doesn't just sit there, it changes the way infrared light moves through the air. Add methane, carbon dioxide, and water vapor in various amounts, and the atmosphere becomes a maze for heat to navigate. Clouds complicate everything. A bright, high cloud deck can bounce starlight back into space, cooling the surface. A thick, low blanket can trap heat like a lid on a pot. With enough layers, the vertical temperature profile can bend, flatten, or invert, changing which spectral lines look strong or weak to a telescope. Precision matters, but so does humility. Climate models are only as good as the chemistry and physics they include. On Earth, we test models against weather balloons, satellites, and ocean buoys. For a distant exoplanet, the tests are fewer and the unknowns are many. That's why Webb's different instruments, and eventually other observatories, have to attack the same target from multiple angles. Catch the planet during transit to read the starlight filtering through its limb. Catch it before and after transit to look for reflected light. Catch it when it slips behind the star to isolate the planet's own thermal glow. Each observing mode slices the problem differently, and the overlap builds trust. There is another slippery word in this conversation: certainty. 99.7% feels like a verdict, but it is only a confidence level attached to a particular bump in a particular dataset under a particular set of assumptions. Change the treatment of star spots, tweak the noise model, include a new molecule with overlapping lines, and the number can slide. This is not weakness, it is the engine of progress. As teams reanalyze the same light with sharper tools, signals that were fuzzy come into focus or fade. What survives is what we can't get rid of. The star itself is a character in the story. Red dwarfs like the one in Leo are thrifty with fuel and can live for hundreds of billions of years. That longevity gives any orbiting ocean all the time in the universe. But youth is noisy. Many red dwarfs, especially early in life, toss flares and blasts of ultraviolet radiation into space. Those tantrums can split molecules, drive strange photochemistry, and even strip away atmospheres. Whether K2 to 18b's sky is old and calm, or still recovering from a rough childhood is part of the puzzle. If the star has quieted, and if the planet's gravity and magnetic field have held the air close, then long-term stability is plausible. Let's imagine the ocean for a moment, not to romanticize it, but to understand it as a machine. A global sea under a hydrogen-rich sky would be dark in the depths, and dim even near the surface, since red dwarfs emit more in the infrared than in the blue. Photosynthesis, if it exists there, might favor pigments tuned to long wavelengths, harvesting reddish light. But life does not require sunlight. Hydrothermal vents at the seafloor could pump hot, mineral-rich water into the cold ocean, creating chemical gradients that microbes love. On Earth, entire ecosystems thrive like this, miles below the surface, drawing energy from rocks and water rather than sunshine. If such chemistry runs on K2 to 18b, it could leave atmospheric fingerprints, gases that are hard to maintain without a constant source. This is where biosignature thinking gets creative. Instead of chasing one life gas, scientists look for sets of gases that don't play nicely together unless replenished. They track the ratios and the context. How much total hydrogen is in the sky, how thick the cloud deck is, how hot the upper atmosphere runs under the star's ultraviolet light. They watch for imposters' volcanic gases, photochemical byproducts, or exotic pathways that could fake a biological pattern. The trick is not to eliminate every non-biological possibility. It is to make the non-biological options so baroque, so fine-tuned, that biology becomes the simplest explanation left standing. There is a social side to all this. Science is a conversation across teams that don't share an agenda beyond the truth. One group posts a tentative result, another tries to reproduce it with an independent pipeline. A third asks whether the star's activity could have fooled both. A fourth proposes a new observation that would cleanly separate the possibilities. When the dust settles, everyone updates their priors. The process can feel slow if you crave headlines, but it is the only way to turn maybe into what happens if the most exciting hint fades. Then the field tightens its aim. The lesson is not, don't be excited, but aim your excitement at the right target. If the sulfur route stalls, carbon chemistry may still sing. If a Hycean ocean is less likely, a different class of sub-Neptunes might rise. Webb is not a one-shot wonder. It is a decade-long factory for spectra, and each spectrum is a data point in a new map of habitability. Even a null result sharpens that map. When you hear that a planet might be more habitable than Earth, translate the hype into hope. Bigger is not better for us, but it might be better for microbes. Stranger is not scarier, it is more informative. And certainty is not the starting point, it is the prize after careful work. Somewhere in the spectra of these dim red stars and their hidden oceans, a stable chemical rhythm may be waiting, a rhythm that cannot be played by rocks alone. Whether K2 to 18b carries that rhythm or merely points us toward the next stage, it has already done something historic. It has taken the idea of life beyond Earth out of philosophy and placed it into measurement. Think of Webb's instruments as a trio of exquisitely tuned ears, each listening to a different register of the same cosmic song. Nearest hears the high notes, Near-spec spans the broad middle, and Miri listens to the low, warm tones where heat itself speaks. When K2 to 18b crosses its star, those ears detect tiny changes parts per million in brightness and turn them into spectra, long ribbons of information that encode what the atmosphere lets through and what it blocks. One clean transit is useful. A stack of transits, gathered at multiple wavelengths, turns hints into patterns and patterns into measurements. Behind every colorful plot lies an unglamorous fight against systematics. Detectors warm as they work. The telescope breathes when it enters and leaves sunlight. Pixels age. The star's face rotates, bringing spots in and out of view. Pipelines track these quirks and subtract them with careful models. Teams often run independent reductions on the same raw data, like detectives comparing notes from separate interviews. Agreement builds confidence. Disagreement is a clue that something subtle is still at play. From spectra to chemistry is a leap you make with retrievals. A retrieval code does not assume one atmosphere and declare victory. It explores a vast parameter space, temperature profiles, cloud properties, and gas abundances, and asks which combinations best reproduce the data. The output is not a proclamation, it is a probability landscape. Peaks mark plausible atmospheres, valleys mark ones the light rejects. When methane and carbon dioxide climb to the top together, and ammonia stays low, the Hycean picture gains weight without anyone ever typing the word life. The much-discussed sulfur compound sits in this landscape as a tentative blip. To test it, you want observations in bands where imposter molecules fall silent. You also want data outside transit, because a planet's own thermal glow at infrared wavelengths helps fix temperatures and cloud heights. Put those pieces together, and the retrieval has less room to fake a biological ingredient with purely physical tricks. If the feature persists across modes, you tighten the priors and ask whether any geochemical pathway can keep it afloat for long spans of time. Life is only one engine that can drive disequilibrium. Volcanoes belch, lightning cracks. Ultraviolet light shreds molecules and rebuilds them into strange cousins. In a hydrogen-rich sky, laboratory chemistry suggests families of complex hydrocarbons can form, drift, and rain out, creating hazes that reshape the spectrum. That is why the most convincing case will not hinge on a single gas. It will rest on choreography, a suite of molecules whose combined behavior resists non-biological explanations over years of repeated observations. Consider the planet's size again, because physics never lets you forget it. With a radius about 2.5 Earths and a mass several times larger, gravity presses the lower atmosphere into a dense, warm layer. Scale height, the vertical distance over which pressure drops by a factor of E, can be large in hydrogen, helping spectral features stand out. But if clouds sit high and thick, they flatten everything, smearing out lines like fog on a window. The balance between clear windows and opaque decks becomes the story, because that balance decides which molecules we can actually see. Future observations are already queued. Additional transits with other instruments will aim at the same bands to check repeatability and at new bands to break degeneracies. Secondary eclipses, when the planet slips behind the star, will isolate the planet's thermal emission and help pin down temperatures. Phase curves, the faint variations as the planet shows different faces over its orbit, can hint at winds that move heat from day to night and reveal how deep those winds reach. Each of these adds a stitch to a growing fabric. The tighter the weave, the fewer places a false positive can hide. There is also strategy in target selection, and K 2 to 18b illustrates it. Bright host stars help because more photons mean better precision. Shorter orbital periods mean more transits per year, accelerating the pace of evidence. Quiet stars are a gift because they simplify the noise model. A good target is not only intriguing, it is cooperative. As the field matures, catalogues of sub-Neptunes and super-Earths around nearby red dwarfs will become triage lists that answer a practical question. Which worlds deserve dozens of hours of our very best instruments? Suppose, months from now, the data lean firmly toward a Hycean ocean with active carbon chemistry and a persistent outgassing of a sulfur compound we struggle to explain without biology. What next? The claim would not be, "We found fish." It would be, "We found a stable atmospheric pattern best explained by continuous production of certain gases in an environment compatible with liquid water." That sentence would not end the story. It would begin a new one, steering searches towards similar planets where the same chemistry might appear. And if the opposite happens, if the sulfur hint fades, and the methane plus carbon dioxide pair can be matched by a clever non-biological model, the result still pushes the frontier. We would have learned how hydrogen skies sculpt spectra, how clouds hide and reveal, and how to avoid being fooled next time. The method is not a coin toss between triumph and failure, it is a ratchet. Each turn locks in knowledge that does not slip back. Across all of this, keep a simple image in mind: a dim star, a dark planet, and a thread of light stretched across space. In that thread is weather and climate, chemistry, and maybe metabolism. Our instruments translate thread to numbers, numbers to models, and models to understanding. The wonder is not that the process is slow. The wonder is that it works at all, that from so far away, with nothing but photons, we can begin to tell whether an ocean breathes. Begin with the moment this world stepped into our story. A decade ago, NASA's repurposed Kepler mission, K2, watched a small patch of sky in Leo and recorded tiny clockwork dips in a dim red star's light. Each dip meant a planet was crossing the star like a moth brushing a porch lamp. Astronomers tagged the world, K2 to 18b, measured its period and size, and filed it among thousands of finds. That is how discovery often begins, a whisper, not a shout. The second act weighed the planet. Using precision spectrographs on Earth, observers tracked the star's slight wobble as K2 to 18b tugged on it. Pairing mass with radius produced a density too low for a scaled-up Earth. The better fit was a mini Neptune, a solid interior wrapped in a lighter envelope rich in hydrogen and other gases. Our solar system has no planet in this in-between class, which is exactly why it seized attention. Nature had built a type we had never met at home. Then came water vapor. Years before Webb launched, the Hubble Space Telescope studied starlight that had filtered through K2 to 18b's atmosphere and picked out a broad feature consistent with water. It wasn't an image of clouds, it was a spectral fingerprint, like hearing a piano note and recognizing the key. That hint lifted K2 to 18b onto the shortlist for Webb's early exoplanet targets. If Hubble could glimpse water in broad strokes, what might Webb resolve with sharper eyes and a wider palette? Webb's first passes gave the story a new shape. Methane and carbon dioxide appeared together, while ammonia seemed scarce. In a hydrogen-rich sky, that trio points to conditions where carbon prefers to live as CH4 and CO2, and where an ocean below could be exchanging gases with the air above. That is the Hycean idea: hydrogen overhead, a deep global sea below, and an energy balance that keeps large regions temperate over long spans of time. Now ask the harder question: how is the atmosphere stacked? Imagine rising through layers. Near the bottom, pressure is high, and temperatures are warm. Higher up, pressure falls and temperatures can bend or even invert. Clouds gather in decks, each forming where a different substance condenses. During a transit, the starlight we measure skims those limb layers, so the spectrum depends on cloud height, haze thickness, and how sharply temperature changes with altitude. A clear, deep view makes molecular lines stand tall. A high, bright cloud deck flattens everything, hiding chemistry the way fog hides a skyline. This is why timing and diversity of observations matter. Revisit the same planet months apart and you test whether star spots or flares fooled you the first time. Use independent instruments and you test whether a calibration quirk created a ghost feature. Watch during transit to sample the limb. Watch during secondary eclipse when the planet slips behind the star to isolate the planet's own thermal glow. Add phase curves, the gentle brightening and dimming as the planet shows different faces, and you learn how winds move heat from day to night. Each mode slices the puzzle from a new angle. The overlap builds trust. Why did this one world become a stand-in for the larger question? Practicality helps. The host star is bright enough for precise work, and the orbit is short enough to offer multiple transits per year. A hydrogen atmosphere also has a large-scale height, which makes spectral features deeper and easier to detect than in a thin, Earth-like sky. But there is a philosophical draw. If life can arise in a dark, planet-spanning ocean, under a puffy sky, around a small, cool star, then the universe's habitable real estate may be far larger than the narrow band we once imagined. Healthy skepticism, though, is not a mood, it is a method. Could volcanoes maintain methane at the levels Webb infers? Perhaps, but keeping methane high for long without the right companions, such as carbon monoxide in specific ratios, is difficult without biology or very special geochemistry. Could photochemistry in a hydrogen sky build complex hydrocarbons whose overlapping lines masquerade as something else? Possibly, which is why teams push for broader wavelength coverage, where imposters grow quiet and real candidates stand out. Could high clouds be hiding key features? Yes, that is why thermal emission and phase curve data matter, because they help anchor temperatures and cloud heights without relying only on the limb view. Consider the star's early life. Red dwarfs often flare when young, tossing ultraviolet blasts toward their planets. That radiation can split molecules, strip atmospheres, and drive odd chemistry. Yet time brings calm. Many red dwarfs settle down, and a sufficiently massive planet can hold onto a thick envelope through rough weather. If K2 to 18b kept its air and its ocean, the star's long, quiet middle age could provide billions of steady years and eternity for chemistry to explore, test, and iterate. So what would success look like in the next round of data? Not a single smoking gun line, but a coherent story that survives every attempt to break it. The same methane and carbon dioxide strengths reappear in multiple transits. Temperature estimates from thermal emission match what the transmission spectrum implies. Ammonia stays low where models predict little. And if a candidate sulfur compound truly is present, it shows up in bands where alternatives fail and persists when different teams reduce the light with different pipelines. At that point, the simplest explanation left standing starts to look biological. And if the tapestry frays, then we recalibrate and aim at the next best targets. Webb's calendar is already filled with sub-Neptunes around quiet, nearby red dwarfs, each a chance to learn. The craft we hone on, K2 to 18b, separating star from planet, instrument from signal, and model from measurement will apply to all of them. Somewhere in that growing sample, the chemistry will line up in a way rocks cannot easily fake. When that happens, the sentence will not be, "We found fish." It will be, "We found a stable atmospheric pattern, best explained by continuous production of certain gases in an environment compatible with liquid water." Think of Webb spectra as a language of light. Every gas in a planet's sky absorbs at specific colors, leaving tiny missing notes in the rainbow. When K2 to 18b crosses its star, those notes line up into a melody. Methane and carbon dioxide are loud, ammonia is faint. That combination fits a warm, hydrogen-rich atmosphere that may sit on top of a deep global ocean. Yet light can mislead impatient listeners. Star spots can mimic features, instruments can drift, hazes can flatten lines. So before anyone whispers life, scientists try to rule out the ways the universe can fool them. Start with the star. Red dwarfs have mottled faces, cool spots, and bright faculae that rotate in and out of view. Because spots change the star's color, they can impose false patterns on a transmission spectrum. Teams model the star's surface and monitor its brightness over weeks to recover the rotation period. If the depth of a spectral feature waxes and wanes with that cycle, caution flags go up. If the feature stands steady across months while the star itself changes, confidence grows that the signal belongs to the planet's air. Then, the instrument. Webb is stable, but not static. As it warms and cools, focus shifts by hair-breadth amounts. Individual pixels respond slightly differently to light. Engineers build calibrations from standard stars, use reference pixels to track, drift, and apply statistical corrections that capture the instrument's quirks. What remains after all of that must be repeatable across observing runs and consistent across independent reductions by different teams. Chemistry brings its own tricks. In a hydrogen atmosphere, ultraviolet light breaks methane apart and rebuilds it into heavier hydrocarbons that clump into hazes. Hazes act like a gray veil. Thin veils let molecular lines peek through. Thick, high veils flatten everything. The fact that methane and carbon dioxide are both visible implies windows in the veil, clear paths between cloud decks where starlight reaches deeper layers. If an ocean exists, those layers can exchange gases with the sea below, imprinting the air with a stable, planet-wide chemistry. Vertical structure matters as much as ingredients. Imagine climbing through the sky, high up. Haze warms under starlight. Below that, temperatures cool, then rise again as pressure increases. Each bend in that profile changes which lines look strong or weak. Retrieval codes explore thousands of such profiles and many mixtures of gases and clouds, asking which combinations reproduce the entire spectrum. When different teams, using different codes, land on similar answers, it suggests that the light itself is forcing the solution. Why not just hunt for oxygen and declare victory? On a hydrogen world, free oxygen is short-lived. It reacts away. Life, if it thrives there, may never make an oxygen-rich sky. So biosignature thinking shifts from one magic molecule to sustained disequilibrium, methane coexisting with carbon dioxide in specific ratios, fragile sulfur compounds that ultraviolet light would destroy unless replenished, and a lack of companion gases that would otherwise accumulate if geology alone ran the show. Biology is then the simplest engine left to keep the pattern going. What would decisive progress look like? First, repeatability. See the same features in multiple transits months apart. Second, breadth. Observe at wavelengths where imposter molecules fall silent, but the candidates should grow. Third, context. Measure the planet's own glow during secondary eclipse to lock down temperatures and cloud heights, so the retrievals cannot cheat by sliding profiles around. Fourth, dynamics. Collect a phase curve, the slow brightening and diming as the planet shows different faces to learn how efficiently winds carry heat from day to night. Together, Those tests turn a hint into a narrative that is hard to fake. Now step back. K2 to 18b is not a lone curiosity. It is part of a new census. Dozens of nearby sub-Neptunes orbit quiet red dwarfs bright enough for Webb. If several show the same methane plus carbon dioxide pattern and similarly low ammonia, and if one or two display persistent hints of fragile sulfur gases, the prior that hydrogen oceans can host metabolism will rise. If the pattern appears once and fades, we learn how nature tricks us and move on with sharper tools. Beyond spectra lies a near future where we can watch weather. Coronagraphs on upcoming space telescopes will suppress starlight and let us image warm, close-in planets directly. For Hycean candidates, mid-infrared images can map cloud tops and circulation. Combine those maps with spectra, and instead of inferring climate from a handful of lines, we will see winds, hotspots, and perhaps seasonal changes. That will not reveal who lives there, but it will show whether the stage is set for chemistry to run without interruption for ages. Science has a human tempo. A rumor starts, a preprint appears, headlines sprint ahead. Meanwhile, researchers reprocess the light with independent pipelines, poke at assumptions, and design a cleaner test. The best outcome is not the fastest claim. It is the claim that survives a year of energetic, skeptical attempts to break it. That is how certainty is earned. And still, wonder remains the reason we try. If K2 to 18b truly wears a hydrogen sky over an old, deep ocean, energy must flow somewhere in that dim water. Vents could lace minerals into the sea. Slow overturning could carry nutrients up and waste products down. Microbes, if they exist, would be tiny engines, exhaling gases that drift upward, slip through cloud gaps, and carve repeatable notches into starlight. Those notches crossed 120 light-years to reach Webb's mirrors. From them, we are learning to read a new book, not about us, but about the ways life might keep chemistry out of balance on worlds we will never touch. Begin with a smell you already know. Stand on a windy pier. Breathe the sharp, clean tang of the ocean, and you are meeting dimethyl sulfide. On Earth, this small sulfur molecule rises from the sea when microscopic plankton live, feed, and burst. Seabirds follow its scent across empty water. Cloud droplets use its oxidized cousins as seeds. The ocean breathes, chemistry stirs, and the air gains a faint signature of life. That is why even a tentative hint of a related sulfur compound in a distant planet's sky made people lean forward. It is not proof, but it rhymes with something we know. Yet sulfur is a shapeshifter. Volcanoes belch it, lightning forges it, ultraviolet light tears it apart and stitches it into new forms. The scientific question is not whether sulfur can exist, of course it can. The real question is whether a fragile sulfur compound can persist at the levels we think we see, without a steady source that looks suspiciously biological. On Earth, dimethyl sulfide lasts hours to days in sunlight. Its steady presence means constant renewal by marine life. On a hydrogen-rich world around a red dwarf, the exact lifetime would differ because ultraviolet light, temperature, and competing reactions shape the chemistry. But the logic holds. If a delicate gas keeps showing up, something must be making it again and again. Context is the judge. Teams estimate the star's ultraviolet output because UV sets the destruction rate. They model vertical mixing winds that lift gases from a hypothetical ocean to the high limb that transit light samples. They check which companion sulfur species should appear in any non-biological scenario. If those companions are missing while a fragile candidate lingers, geology begins to look strained. If, instead, a plausible stew of photochemistry and volcanism can reproduce the lines, biology retreats to the back row. Either way, the answer is earned with specifics, not slogans. Thermal light sets fresh constraints. During secondary eclipse, when the planet slips behind its star, Webb isolates the dayside's glow. The shape of that glow reveals the temperature profile. If it agrees with temperatures implied by the limb during transit, confidence grows that cloud heights and gradients are pinned down. If it disagrees, say, a hot day side but a muted limb, then high clouds may be hiding chemistry, and the retrieval must be revised. Either outcome shrinks the parameter space and forces the models to match reality. Motion helps too. Phase curves the planet's smooth, brightening and dimming over an orbit show how well the atmosphere moves heat from day to night. A large day-night contrast points to sluggish winds and perhaps patchy cloud cover. A small contrast points to a thick, efficient blanket that smears heat around the globe. Both cases narrow the climate menu. If winds are strong and the blanket is thick, a stable ocean beneath becomes more plausible, because surface swings would be modest and long-term habitability gets a boost. Compare. CAR 218b is one data point in a growing census of sub-Neptunes. Some cousins show glass-clear skies, others are smeared by soot-like hazes. Still others may have lost much of their hydrogen and drifted toward water world status. As Webb stacks spectra, and as Hubble and ground-based instruments contribute, patterns will emerge. If Hycean candidates repeatedly show the methane-carbon dioxide pairing with low ammonia, while otherwise similar planets without oceans do not, we gain a diagnostic, a way to sort worlds by chemistry, not by wish. What comes next is scale. Europe's aerial mission will survey hundreds of exoplanet atmospheres with a uniform playbook, turning isolated case studies into statistics. NASA's Roman Space Telescope will deepen the catalogue of planets and refine host star properties that feed climate models. On the ground, extremely large telescopes will spread starlight into razor-thin rainbows, hunt for fainter features, and measure line shapes that betray winds. Together, these tools will do what science always does when a claim thrills the public: raise the bar, widen the sample, and make the result earn its fame. There is a human tempo beneath the graphs. A graduate student is staring at a noisy spectrum, asking whether the wiggle is real or an artifact. A team lead is choosing between a repeat transit and a fresh target. An engineer is shaving a few parts per million off a detector's drift. None of them knows whether K218b will become our first persuasive sign of life or a famous false alarm. All of them know the only way to find out. Carry forward a simple rule. Biology, if present, should be the simplest long-term engine that keeps the observed mix of gases from relaxing to chemical equilibrium in the face of sunlight, winds, and gravity. If a non-biological engine must be exotic, finely tuned, or precariously balanced to reproduce the same pattern while biology would do it naturally, then life moves from wishful to reasonable. If the opposite is true, we update the priors and point our instruments to the next world that whispers through light. Either way, the search is working because it is teaching us how to listen. Imagine proving that Earth is alive using only starlight. No photos of continents, no radio chatter, only the faint rainbow of our air. What would we look for? We would see water vapor, because oceans breathe. We would find oxygen living uneasily alongside a little methane. A pairing sunlight should destroy unless something keeps refilling it. We would see carbon dioxide in modest amounts, and a temperature profile that bends in ways only a moist, cloud-forming atmosphere can. In short, we would not need cities to know the planet is busy. We would read life from imbalance. Now, take that compass and point it outward. If a hydrogen-rich sky sits above a global ocean, biology does not need to sign its name with oxygen. It can write imbalance elsewhere: methane persisting with oxidized carbon, fragile sulfur compounds that ultraviolet light should destroy unless they are renewed, and a notable absence of companion gases that a purely geological model would naturally pile up. The goal is not a single smoking gun. The goal is a pattern that repeats across time, across wavelengths, and across observing methods until non-biological explanations look contrived. To reach that standard, astronomers design orthogonal tests checks that fail for different reasons if we are wrong. Transmission spectra during transit probe, the limb, the thin ring where starlight skims the atmosphere. Thermal emission during secondary eclipse isolates the dayside's glow and pins down temperatures and cloud heights. Phase curves watch the planet brighten and dim over an orbit, revealing how efficiently winds move heat from day to night. Soon, polarization measurements will test cloud particle sizes and hazes. Each probe bites a different piece of parameter space. When they converge, confidence moves from maybe toward probable. Temperature is more than a headline number. The equilibrium temperature sets a baseline, but chemistry cares about the vertical profile, the exact way heat changes with altitude. A hydrogen blanket puffs the air, so starlight samples a tall slice of sky. If upper layers are hazy and warm, while deeper layers are cooler and moist, the spectrum highlights different molecules at different heights. That is why the best retrievals do not assume a straight line temperature. They let the profile bend, flatten, or invert, and then ask the light which shape it prefers. Pressure is the silent partner. At sea level on Earth, air presses with about 1 bar. On a sub-Neptune, the pressure where the ocean meets the sky could be dozens or hundreds of bars, depending on the envelope's thickness. High pressure pushes water towards strange phases, supercritical states that are neither liquid nor gas. Yet, even then, a temperate layer can exist higher up where water condenses and clouds form. If life needs liquid interfaces, those layers may be its playground, suspended between the deep and the haze. We also need to talk about nitrogen. On Earth, nitrogen is the quiet majority of our air. It sets pressure, shapes climate, and provides the feedstock life turns into proteins. On a hydrogen world, nitrogen may be scarce in the observable layers or locked deeper down. That does not doom life. Microbes can thrive on other chemistries, but it changes which gases are informative. Instead of hunting for nitrous oxide or oxygen, we may listen for subtle ratios among carbon, sulfur, and hydrogen compounds that tell us whether geology alone can maintain the mix. Beware of mirages. Photochemistry under red dwarf light can build complex hydrocarbons that create soot-like hazes. Those hazes mute molecular lines and can mimic a composition that is not really there. Volcanoes can pump methane and sulfur into the air, but they often bring along carbon monoxide in ratios biology would not sustain. Star spots can paint false colors on the starlight, especially if the star rotates slowly enough that spots evolve between visits. Good teams treat every one of these as a hypothesis and try to break it before they believe the planet. Scale matters, and Ca-218b's scale helps us. A large atmospheric scale height makes absorption features deeper. A short orbital period gives many transits per year. A bright, relatively calm star lowers the noise floor. Those three together make this world a training ground for the methods we will carry to the next targets. If the most exciting hint here fades, the lessons will not. They will sharpen the knives we take to the next spectrum and save us from chasing ghosts. Time matters too. Life is patient. Planets evolve. A single transit is a snapshot. A campaign is a diary. Over the next few years, repeated looks can catch seasonal drifts in haze, shifts in cloud tops, or slow changes in methane that trace chemistry settling toward equilibrium, or being pushed away from it again and again. Stability over time is its own clue. Geology can pulse in bursts. Biology tends to hum. The bigger arc is this. We are moving from discovering planets to diagnosing them. The first era asked, how many worlds are there? The second asks, what are they like? The third, which Webb has launched, asks, which ones carry chemistry that should not sit still? And the fourth will ask, can we map their weather and watch their climates work? Somewhere along that arc, the sentence we all wait for will become scientifically routine. This atmosphere shows persistent, multi-wavelength disequilibrium, best explained by continuous replenishment in a stable, water-compatible environment. If that sentence lands on K2-18b, it will be because every alternative wilted under pressure. If it lands elsewhere, it will be because this world taught us how to listen better. Either way, The search is already paying off, not with final answers, but with a new skill, the art of reading lives we cannot see, written in the faintest edits to starlight. Start with the only planet we truly know. If Earth were a distant dot, what would give it away? Not cities or radio chatter. Telescopes cannot resolve those. The giveaway would be imbalance. Our air holds oxygen that should vanish, methane that sunlight should destroy, and water vapor that should condense out, yet persists. Volcanoes and lightning help, but not enough, and not in the particular ratios we measure. Biology keeps refilling the tank. That is the core of biosignature logic. Now widen the lens. False positives haunt this search. Rocks can fool us, so can light. Around some stars, ultraviolet radiation splits molecules and knits them into lookalikes, whose spectral lines overlap with the gases we care about. On worlds with thin or patchy clouds, temperature layers can trick retrievals, shifting features like a mirage. Even star spots can paint color onto starlight and carve dips where none exist. The antidote is redundancy across methods and time. We also learn from near misses. A few high-profile hints of life-related chemistry have lit headlines, then dimmed as teams reanalyzed the light with sharper calibrations and alternative models. Those sagas were not failures. They were rehearsals. They taught observers to preserve raw data, share pipelines, publish noise models, and write predictions that new observations can confirm or kill. Today's Webb teams build on that culture. Claims arrive with caveats and with tests planned in advance. Timescales matter. Geology breathes in pulses, eruptions, impacts, spurts of outgassing while biology hums. If a fragile gas appears once and fades, geology stays in the running. If it persists across orbits and years, despite a star that should destroy it, metabolism becomes the simpler explanation. That is why long campaigns are powerful. A single spectrum is a snapshot. A timeline is a diagnosis that separates weather from climate and accidents from engines. Star type sets the stage. Red dwarfs sip fuel and live for trillions of years, offering stability that sun-like stars cannot match. But their youth is often violent. Early flares and high-energy photons sculpt atmospheres, seed hazes, and alter chemistry before calm returns. Planets that keep thick envelopes through that childhood, thanks to gravity, magnetic fields, or sheer mass, enter a long middle age where oceans can settle and climates can stabilize. That middle age is where habitability becomes testable. Tidal locking is another piece. Close-in planets often show one face to their star forever. The day side bakes, the night side freezes, and a permanent ring of twilight circles between. With a thick atmosphere, winds can shuttle heat from day to night and smooth extremes. Phase curves reveal how well that shuttle works. A small day-night contrast hints at strong circulation and deep cloud blankets. A large contrast hints at sluggish winds or high patchy clouds. Either way, we learn how the climate runs. Magnetism is a quiet player. A magnetic field can deflect charged particles from the star, protecting upper atmospheres from erosion and limiting chemical mayhem in the heights we observe during transits. We cannot yet measure exoplanet magnetism directly for most worlds, but line shapes, auroral candidates, and radio searches offer clues. Models then ask whether the interior could power such a field. A salty ocean, a conducting core, or layered convection that keeps currents flowing for eons. Watch how the pieces reinforce one another. Temperatures from thermal emission constrain cloud heights. Cloud heights tighten retrievals of gas abundances. Those abundances feed climate models that predict phase curve shapes, which we can then check. When the loop closes cleanly, confidence rises. When one piece fights the others, we revise our assumptions and try again. Exoplanet science is less like a single decisive measurement and more like solving a crossword. The right answers interlock. Consider nutrients. Because oceans are not just water, life needs building blocks and energy gradients. On a world with a deep sea and no continents, Nutrients may rise from the seafloor or leak from the interior through hydrothermal vents. That supply depends on geology and on how vigorously the ocean overturns. Slow circulation can starve the surface. Strong mixing can fertilize it. Both regimes leave different atmospheric fingerprints that long-term spectra can, in principle, distinguish. Now return to the provocative phrase, more habitable than Earth. We take habitability personally, but microbes do not. For them, volume and time matter more than beaches. A hydrogen-blanketed ocean world might offer vast, stable habitat layers, immune to ice ages and drifting continents. It would be hostile to humans and friendly to chemistry. If several such planets show repeating, steady disequilibria, the map of habitable real estate will shift away from Earth-like toward unfamiliar, ocean-capped worlds. None of this works without humility about error bars. Teams report not just best-fit values, but credible intervals. They test how results change if you broaden priors, add a missing molecule, or alter the star's spot coverage. They run retrievals blind on synthetic data to see whether pipelines invent lines. These checks reduce the chance that our desire to find life draws it in the noise. The goal is not paralysis, it is rigor, so a positive result still stands when every assumption is jostled. Picture the moment of convergence. Multiple transits agree. Thermal emission matches. Phase curves line up. The same gases recur with the same strengths. Noise models have teeth, and independent teams reproduce the spectrum with their own code. Non-biological scenarios require narrow, implausible fine-tuning to keep a fragile gas alive while suppressing its expected companions. At that point, the most resilient explanation is that something down there is running cycles and refusing chemical equilibrium. That is the promise of this era, moving from wondering whether life exists to diagnosing where it likely thrives. K218b may carry that diagnosis, or it may hand the baton to a cousin. Either way, it is teaching us the grammar of alien climates and the signatures of restless chemistry. With each spectrum, we migrate from metaphor to measurement, from wish to inference, from silence to a careful, evidence-based yes. Start with trust, because that is what a breathtaking claim quietly asks for. A telescope a million miles from home reads a few missing colors in a rainbow and whispers that a distant ocean might breathe. Between that whisper and a headline sit three defenses against self-deception: transparent data, independent teams, and predictions that risk being wrong. When those align, confidence stops being a mood and becomes a measurement. Transparent data sounds simple. It is not. Raw counts from detectors are touched by many corrections. Dark current, flat fields, pointing drift, cosmic ray hits. Good groups publish not only the final spectrum but the steps between, the choices and priors, the corner plots that show what the model surrendered to fit the light. They release open code or exact recipes so rivals can rerun the analysis and ask different questions of the same photons. Truth in science is repeatable, and repeatable means public. Independent teams are less about courtesy and more about stress tests. One pipeline assumes the star's spots evolve slowly, another assumes they change quickly. One lets the temperature profile bend, another lets the clouds fracture into layers. If the core features survive those changes, if methane and carbon dioxide persist, if ammonia stays low, then the signal is not a quirk of one set of assumptions. It is a property of the planet and its star. Predictions are the sharpest tool. A real atmosphere is not a one-note instrument. If the retrieval says methane is strong, it should also say where a methane line will deepen at a longer wavelength Webb has not yet used. If clouds sit high, the thermal glow should be muted in ways a secondary eclipse spectrum can test. If a fragile sulfur compound is present, then its photochemical cousins should appear faintly here and not there. Predictions are how bold claims put skin in the game. Now turn the numbers into metaphors that do not lie. 99.7% is not life found. It is this feature prefers to be real rather than random under the current model. Equilibrium temperature is not exactly 120 degrees, but a baseline. before greenhouse gases and clouds do their work. More habitable than Earth does not mean better for people. It means a larger, steadier volume, where liquid water and gentle chemistry may persist for long spans of time. Humility also means naming blind spots. We do not know how often red dwarf flares sculpt hydrogen skies. We do not know how thick Hycean clouds grow before they flatten the spectrum. We do not yet know how common nutrient cycles would be in global oceans with no continents to erode. These are not excuses. They are the to-do list. The next wave of observations will attack. History keeps balance. Viking landers tasted odd chemistry on Mars and left us arguing for decades about what positive meant. Venus's claimed phosphine flickered as calibrations improved and instruments weighed in. Mars' methane rose and fell with seasons, with instruments, and with assumptions. None of those sagas was a waste. Each taught the field to publish noise models, preserve raw frames, and write tests a fresh dataset can decisively answer. Bayes lurks beneath the poetry. Before a new spectrum arrives, we have priors. How likely life is, how likely it is on a Hycean world, how often geology can fake a living pattern. The spectrum updates those priors. One hint nudges them. A set of consistent, multi-wavelength, multi-method signals shifts them more. The first exoplanet life claim that sticks will not convince because it shouts. It will convince because the odds climbed step by careful step and would not climb back down when prodded. Consider ethics, because discovery does not happen in a vacuum. When a team writes that life is plausible, markets twitch, funding flows, and students choose careers. Overstating certainty burns public trust. Understating it stalls progress. The path forward is clarity. Say exactly what was measured, what was assumed, and what would change the conclusion. Invite rivals, publish the recipe, bet the claim on a prediction the next observation can kill. Meanwhile, the universe waits, indifferent. If C218b wears a hydrogen sky over a deep old ocean, weather will roll whether we interpret the lines or not. Winds will carry heat, hazes will rise and fall, vents will lace the water with minerals, and perhaps microbes will turn gradients into metabolism. Their signatures will ride photons across space, thread webs mirrors, and land in our models as tiny dips that refuse to go away. Here is what success can feel like from the inside. A student reruns last year's data with a stricter noise model, and the features stay. Months later, a new wavelength where imposters are quiet shows the candidate thriving. Thermal emission agrees with the limb view. Phase curves show winds strong enough to keep climate steady. A rival group's independent code lands on the same abundances within similar credible intervals. The paper ends not with exclamation points, but with a plain sentence and a test for the next run. And if not, if the sulfur hint fades, if clouds sit higher than we thought, if geology turns out to be a better chemist than we gave it credit for, then what we gain is sharper ears. The next Hycean candidate will face a tighter gauntlet. The next headline will come with cleaner caveats. The next student will inherit pipelines that manufacture fewer ghosts. The search for life will have done what good searches always do. Remove ignorance, even when it does not deliver the prize on schedule. The telescope keeps listening. The star keeps shining. The spectrum keeps teaching. Somewhere, whether here or in the next system over, a pattern will emerge that rocks cannot easily fake and that models cannot explain away. When that day comes, it will not feel like a surprise. It will feel like the end of a long, careful conversation with light and the beginning of a longer one with life. Imagine the decisive test as a journey with checkpoints instead of a single finish line. The first checkpoint is repeatability. The same spectral features must appear across multiple transits, reduced by independent teams. If methane and carbon dioxide remain firm while ammonia stays muted, the chemistry is not a fluke. It is the planet speaking in a steady voice. The second checkpoint is breadth. Observations must cover wavelengths where imposter molecules grow quiet and true candidates stand tall. The third checkpoint is temperature. During secondary eclipse, when the planet slips behind its star, We isolate its thermal glow and pin down how heat changes with altitude. If those temperatures agree with what the transmission spectrum implies, cloud heights and haze layers lock into place. The fourth checkpoint is motion. Phase curves trace the slow brightening and dimming over an orbit and reveal how well winds move heat from day to night. The fifth checkpoint is context. The star's temperament must be monitored so that flares, spots, and faculae cannot forge false colors. The sixth checkpoint is prediction. A credible retrieval does not fit yesterday's points. It forecasts tomorrow's what lines should deepen at new wavelengths, which windows should open when haze thins, and how the thermal glow should look when the planet vanishes behind its star. What would a positive verdict sound like in plain language? It would say that the atmosphere holds a stable combination of methane and carbon dioxide with low ammonia, sustained across time, that clouds and temperatures are constrained independently by thermal emission, that a fragile sulfur compound persists where sunlight should erase it unless something replenishes it, and that non-biological models can mimic pieces of the pattern only by invoking narrow, finely tuned conditions that collapse when fresh data arrive. What would such a world feel like up close? The sky would be pale and thick, a hydrogen veil laced with high, hazy decks. Winds would flow from day into night in a global conveyor, smoothing extremes. Far below, the sea would stretch unbroken, dark in depth and dim even near the surface. No continents or beaches, only a continuous interface where air and water trade molecules by slow breath. If metabolism exists there, it would not need forests or coastlines. It would need gradients and time. The ocean's engine would run on more than sunlight. At the seafloor, pressure would be immense, and heat would leak from the interior through vents, making mineral-rich plumes that rise, mix, and fall. In that moving water, tiny cells, if present, could harvest energy from reactions between rocks and dissolved gases. Waste products would drift upward, join the air, and etch faint, repeatable notches into starlight sentences we can read from 120 light-years away. Even a negative result moves the field. If the sulfur hint fades, we learn the tricks hydrogen skies can play. If clouds sit higher and thicker than expected, we refine models of haze growth and rainout. If methane and carbon dioxide ratios drift with stellar weather, we learn to fold star spots and flares into climate. Each adjustment tightens the next attempt. Science is a ratchet. Knowledge clicks forward and does not slip back. Scale the lesson outward. Nearby sub-Neptunes around quiet red dwarfs will become a comparative sample rather than isolated curiosities. If several show the same carbon pattern and similar thermal profiles, the case for Hycean stability strengthens. If some diverge, we identify branches on the family tree and ask why they differ. Diversity is not noise. It is information about formation, interiors, and the tug-of-war between sunlight, gravity, and time. A cultural shift is underway. Open data, shared code, and rapid preprints let the community audit bold claims in weeks instead of years. Teams now stress-test pipelines by injecting fake signals, scrambling timestamps, and running blind retrievals on synthetic atmospheres so software cannot dream lines into existence. The result is confidence that a surviving signal has earned its place. Behind the methods is a simple human truth. We are pattern seekers, and the cosmos is generous with patterns. A cautious framework protects us from seeing faces in clouds. It insists that lines recur where they should, vanish where they must, and scale with temperature the way physics demands. It asks for patience when data are quiet, and for wonder only when redundancy leaves doubt nowhere to stand. Finally, imagine the quiet after confirmation. There will be no fireworks, only a plain sentence. A distant atmosphere refuses chemical equilibrium in ways most simply explained by continuous replenishment compatible with liquid water. The day after, nothing on Earth will look different. Yet, everything will be reframed. Life will look less like a miracle of scarcity and more like a habit of the universe. Our night sky will feel less like a backdrop and more like a neighborhood. The question will shift from whether life exists to where it thrives and how often it awakens. That shift matters at home. Knowing that metabolism blooms under alien skies changes how we think about resilience, climate, and rarity. It reminds us that Earth is one member of a wider class, worlds where energy gradients meet time and stability. It makes exploration feel like kinship rather than conquest, and it hands science a responsibility. Measure carefully, speak precisely, invite scrutiny. The first confirmed sign of life beyond Earth must be solid enough to carry the weight of history. Between here and that sentence lies work, boring, beautiful, repetitive work, more transits to stack, more wavelengths to explore, more models to test and rebuild. That is the rhythm of discovery. It is slow by design, so that when the music swells, we can trust the notes. If this particular world earns the verdict, we will celebrate. If it passes the torch to a cousin, we will celebrate the map it drew. Either way, the art of reading light will deliver what it promised, a way to learn who shares the universe with us, written in the faint edits that life makes to starlight. Picture how scattered clues become a climate. The first spectrum hints at which gases exist. A second nails down clouds and hazes. A third, months later, checks whether the picture holds when the star is calmer, the instrument is cooler, and the algorithms are stricter. With each pass, the planet stops being a rumor and becomes a system, a sky with layers, a circulation with habits, a chemistry with reasons. Orbits set the rhythm. K2 18b loops its red dwarf in about a month, close enough that tides likely lock one face today and the other tonight. Locking is not a death sentence. A thick hydrogen blanket can ferry heat around the globe. Along the terminator, the ring of permanent sunset temperatures may hover in tolerable ranges, even if the substellar point is warm and the night side is cold. Phase curves test this balance by tracking the planet's slow brightening and dimming across an orbit. A small contrast signals efficient circulation. A large contrast points to sluggish winds or patchy high clouds. Interiors push upward on what we see. A sub-Neptune may hide a volatile rich mantle, a very deep ocean, and a supercritical layer where water behaves like a dense vapor and a thin liquid at once. Chemistry crosses those boundaries. Dissolved gases percolate upward. Clathrate ices trap them and release them later. Convection ferries heat and material. If a rocky seafloor is active, hydrothermal vents seed the water with metals and sulfides. In that dim environment, if cells exist, they would feed on redox gradients and turn them into metabolism. Now translate physics into observables. Hydrogen gives a large-scale height, the distance over which pressure falls by a factor of E, so absorption lines can be deeper than on an Earth-like world. Clouds and hazes fight back by flattening features. Retrievals weigh both at once. If a model needs clouds so high and thick that almost no light should reach methane, and carbon dioxide-rich layers, yet those gases still appear, the model must yield. If the gases vanish whenever clouds are raised, the original reading may have leaned too hard on clouds to explain the lines. Noise is not the enemy. Uncharacterized noise is. Teams inject synthetic lines into raw counts to test whether pipelines recover them. They scramble timestamps to make sure gentle drifts are not inventing features. They run blind, hiding key parameters so human hopes cannot nudge a fit. When a feature survives that gauntlet, it graduates from rumor to measurement. Calibrating the star is just as crucial. Red dwarfs wear cool spots and bright faculae. As the star rotates, its color wobbles. Those wobbles can masquerade as planetary chemistry. Long, visible light monitoring maps the rotation period and activity cycle. If a spectral dip grows and shrinks with the star's mood, raise the caution flag. If the dip holds steady while the star changes, confidence rises. Nutrients matter, because oceans are not just water. On Earth, continents grind down, and rivers ferry phosphorus and iron to the sea. A world with no continents must mine its interior. Hydrothermal circulation can supply elements, but only if rock and water meet. If high-pressure ices wall off the seafloor, contact may be limited. Fractures, hot plumes, or mantle overturn could punch through. Each case leaves different atmospheric fingerprints over time, subtle shifts in trace gases that long campaigns can separate short bursts from steady sources. Language shapes expectations, so we choose it carefully. A candidate biosignature is not life. It is a gas or pattern hard to sustain without a steady source in water-compatible conditions. 3 sigma is not certainty of organisms. It is a statement that, under explicit assumptions, random noise would imitate the feature only a few times in 1,000. Precision is not pedantry. It is the scaffolding that keeps wonder from buckling. What would a decisive refutation look like if broader wavelengths shift the supposed sulfur line into a better match for a non-biological molecule? Biology steps back. If thermal emission demands temperatures inconsistent with keeping a fragile gas aloft, the story loosens. If independent teams, using fresh calibrations and different noise models, cannot reproduce the feature, the signal returns to the noise floor. That is healthy. It prevents belief from outrunning measurement. What would strong support look like? Repeated transits months apart with consistent methane and carbon dioxide strengths, low ammonia, and a fragile sulfur cousin recaptured at predicted wavelengths. Thermal spectra that lock down cloud heights and temperatures consistent with the transmission view. Phase curves showing winds strong enough to smooth extremes and support a long-lived ocean. A set of negative detections, companion gases geology should produce, but that remain missing that makes a geological explanation increasingly brittle. Zoom out to the next decade. Webb will keep stacking photons. Europe's Ariel will survey hundreds of atmospheres with a uniform playbook, turning anecdotes into statistics. NASA's Roman will refine host star properties and expand the catalogue. Giant ground telescopes will carve thinner lines, catch Doppler shifts that betray winds, and maybe glimpse weak auroral candidates. Later, the Habitable Worlds Observatory aims to image Earth-sized planets around Sun-like stars and steal spectra from their pale light, meaning rides alongside method. If a stable, living pattern shows up in a hydrogen sky, we learn that metabolism does not require continents or blue daylight, only energy gradients and time. If it does not, we learn that ocean worlds are chemically subtle, and that nature enjoys misdirection. Either answer moves us, either answer sharpens the questions we ask next. Hold one image as we press on. A quiet star in Leo, a dark world crossing it, and a filament of light stretched thin by distance. Inside that filament is weather, chemistry, and perhaps breath. We will read it line by line until the mystery either dissolves or hardens into certainty. Either way, the night will feel less like a backdrop and more like a conversation we finally learn to hear. Begin with how such a world forms. Around a newborn star, a disk of gas and dust whirls like a slow hurricane. Pebbles stick into boulders, boulders into protoplanets, and a rocky core assembles first. If that core reaches a few Earth masses while gas still lingers, it begins to drink from the disk. Far from the star, water ice is abundant, so the planet stockpiles water and other volatiles along with hydrogen and helium. Closer in, the mix is hotter and drier. The timing of growth sets the recipe. A core that grows early and far out tends to carry a wetter interior and a puffier sky. Migration quietly sculpts what we end up seeing. Many cores likely assembled beyond the frost line and then drifted inward under gentle gravitational nudges from the disk and from sibling planets. Drift too near the star and the envelope cooks off. Linger too far and the planet stays cold and bulky. Park in the sweet zone and you keep a hydrogen blanket light enough to puff the sky yet heavy enough to last for billions of years. Once the disk disperses, two forces reshape the blanket: starlight and the planet's own heat. High-energy photons chip away at the top in a process called photoevaporation. Meanwhile, the warm interior leaks heat for eons. That glow can loft the atmosphere and help it escape. This is core-powered mass loss. Together, These processes help explain the Radius Valley, a gap between bare, rocky super-Earths and puffy sub-Neptunes. Some worlds lose their thin envelopes and shrink. Others keep enough gas to stay bloated and cloudy. Inside, pressures become surreal. Water moves through exotic states, high-pressure ices with unfamiliar crystal structures, and a supercritical phase that is neither liquid nor gas. A deep global ocean may sit above those layers, with no continents to interrupt it. If rock meets water at the seafloor, chemistry wakes up, minerals dissolve, vents roar, and redox gradients bloom. If high-pressure ice walls off the rock, the ocean must be fed through fractures and hot plumes that punch through the barrier. Either way, the interior controls the diet of the sea, and the sea shares that diet with the sky. We infer this hidden architecture from two numbers that sound simple but speak volumes: mass and radius. Combine them, and you get bulk density. Too low for rock alone means there must be volatiles and gas. Add Webb spectra and possibilities separate. A hydrogen-rich sky with methane and carbon dioxide, but little ammonia, points away from a dry, rocky world and toward a volatile-rich one with an active exchange between ocean and air. Star age matters because the early years are loud. Red dwarfs flare, and their winds blow hard. A planet that kept its envelope through that stormy era likely started big or orbited just far enough out to dodge the worst. As the star calms, haze production slows, clouds settle, and the climate trades chaos for habit. That middle age is the era we hope to observe, the long, quiet stretch when chemistry can persist and write a stable signature into the air. The climate we reconstruct will not feel like home. With a dim red sun and a hydrogen veil, daylight skews red and infrared. The sea is likely dark and deep, lit dimly near the surface and black below. Photosynthesis, if it evolved, might use pigments tuned to longer wavelengths than green. But life does not require light. Chemistry at vents can power metabolism in total darkness, as it does on Earth's abyssal plains. If that engine runs, its exhaust can drift upward, slip through cloud gaps, and etch repeatable notches into starlight for our telescopes to read. Now, connect formation to habitability. A planet born rich in water and protected by a moderate envelope can offer stability that rocky worlds struggle to match. No continents means no ice ages triggered by wandering landmasses. No thin sky means temperature swings are muted. A thick blanket and a deep sea turn weather into a steady hum. Stability over time is the currency life loves, because evolution is a long game that rewards patience. Nature, however, allows detours. Too much hydrogen and surface pressures could crush delicate interfaces. Too little, and the ocean might freeze or boil away. Migration that is too rapid can bake out volatiles. Migration that is too slow can strand the world cold and dim. Our task is not to insist on a single path, but to ask whether the measured atmosphere fits any path that ends in long-lived water and gentle chemistry. If it does, habitability moves from fantasy to forecast. Formation, migration, loss, and interior structure sound like theory, but they lead to tests. If the envelope is modest, phase curves should show efficient heat transport rather than extreme day-night contrasts. If high-pressure ice walls off the rock, certain metal-bearing gases should be scarce. If vents feed the ocean, trace compounds may drift upward in ratios geology alone struggles to maintain. Each is a small lever. Together, they can pry open the black box. In the end, an origin story is not decoration. It tells us whether the present is fragile or durable. A delicate climate that survives only by coincidence is unlikely to host persistent disequilibria. A robust climate with broad margins can. Webb is giving us the present tense. Formation models give us the past. Put them together, and we glimpse the future, a world that can stay kind to chemistry long enough for life. To try, fail, and try again, until it sticks. Begin with the quiet mechanics of certainty. A strong claim is an itinerary, not a finish line. First verify the light, then the instrument, then the star. then the chemistry, then the story they form. At each step, ask what would make this fail. If many things would, you wait. If fewer and fewer would, confidence grows. A team can schedule 2 transits and reverse instrument order so drift cannot mimic gas lines. Another group can inject fake signals and confirm the pipeline does not invent features it wants to see. A third can monitor the star in visible light for months to remove spot-driven color changes from the spectrum. None of this is glamorous. All of it turns hints into measurements. When we say habitability, we mean lasting liquid water and gentle chemistry that lets complex molecules survive. On a hydrogen-rich world, that zone may sit in a temperate atmospheric layer, or in an upper ocean where conditions are kind. Life could float there, feeding on dissolved gases and nutrients that rise from below. Vents can supply redox energy without sunlight. Isotopes add a future check. Living systems often prefer lighter isotopes. With enough precision, ratios in carbon or sulfur could betray metabolism. Time is the honest witness. A fragile sulfur cousin should fade quickly unless replenished. Reappearance with similar strength, months apart, points to a humming source. If the line waxes and wanes with star activity, the star is likely responsible. Either result is progress. Geography without continents favors stable circulation. Winds face no mountains, so a global conveyor can share heat around the world. Along the Terminator, permanent evening may host a wide band where temperatures stay moderate and clouds open. Predictable windows into deeper layers. If retrievals keep landing on the same cloud heights and similar methane to carbon dioxide ratios across seasons, we are reading climate, not noise. Consider failure modes. Meteoric dust can add odd sulfur briefly, but not on a clock, and not at the same depth each time. A mega eruption could spike gases, but it should drag companions that telescopes can check at nearby wavelengths. Instrument quirks could fool one pipeline, but not several different ones that agree within their credible intervals. Soon maps will join spectra. Coronagraphs will outline bright belts and dull zones. Mid-infrared images will locate dayside hotspots. If the dayside glows less than models expect while transmission still shows strong methane and carbon dioxide, high reflective clouds become the simple fix. Cross-checks either tighten the picture or tear it down. Both outcomes are healthy. The caution pays a philosophical dividend. When a signal survives a trial built to kill it, we also learn what it is not. It is not star paint, not software bias, not a cloud trick, not a mistaken molecule. The space of alternatives collapses. The remaining explanation becomes informative, showing how a hydrogen ocean can breathe under a red sun. Scale matters. A world 2.5 Earth radii offers more volume, where gentle chemistry can run for ages. If life is a numbers game between opportunity and time, Hycean planets may stack the deck even if they never grow coastlines. If spectra catch that rhythm on one world, the prior that many others hum, the same tune will rise. Hold humility close. We could be staring at the cleverest false positive yet. The correction would still be a win. The first confirmed life signal must carry culture and education on its back. It needs to be unbreakable. We earn that by trying to break it until it refuses to break. Keep one image at the end. A dim star in Leo, a dark world crossing it, a thread of spectrum like a poem with missing words. We are learning to read the absences. If a living sea lies beneath that sky, its breath is already in our hands, as tiny notches no rock can fake. If not here, then elsewhere. Either way, the method improves, and patience is how we listen. End with the truth that matters. A number can spark a headline, but a method earns belief. 99.7 is not a prophecy. It is a checkpoint on a longer road. What the James Webb Space Telescope has given us is a repeatable way to listen for metabolism across light years, using nothing but missing colors in a rainbow. If C218b carries life, it will reveal itself by patience. The same gases recurring, the same temperatures agreeing, the same patterns holding while every alternative cracks under scrutiny. Think about how far we have come. A dim red star in Leo flickers as a planet glides across its face. Kepler and Cartu caught the dips. Ground spectrographs weighed the world. Hubble glimpsed a broad water feature. Webb split the light thin and found methane with carbon dioxide and little ammonia. From that scaffolding, scientists built tests no press release can rush. Re-observe months apart. Stretch the spectrum into new wavelengths. Catch the planet's own glow and watch its slow brightening and dimming across an orbit. You do not need to speak statistics to feel the discipline. Imagine reading a diary written in ink that only appears under certain lamps. You try a blue lamp, then a red one, then a faint infrared. If the same sentences show up under all of them, in the same place, with the same weight, you trust the story more than you trust any lamp. Webb is those lamps. The atmosphere is the diary. Our job is to refuse easy readings and keep turning pages until the words stop shifting. Now strip more habitable than Earth of human comfort. It means volume and time. It means a steady, planet-wide ocean under a thick blanket that dulls extremes and protects chemistry from wild swings. It means that microbes, if present, could find niches that never dry out or freeze solid for geologic ages. It does not mean beaches you could walk or air you could breathe. It means a factory floor where tiny engines can run without interruption long enough for evolution to do slow, fearless work. There is humility in this, and joy. Humility, because we might be staring at the cleverest false positive the cosmos has yet handed us. Joy, because even if a sulfur hint fades and the spectrum collapses into ordinary chemistry, we will have learned to hear more quietly, to measure more cleanly, to argue more honestly. That is how science wins, even when a claim loses. It replaces ignorance with method, and method with understanding. Carry forward the map this world has already sketched. Nearby sub-Neptunes around calm red dwarfs are not afterthoughts. They are laboratories. If several show the same carbon pattern and similar temperatures, habitability on hydrogen oceans becomes a family trait rather than a rumor. If they diverge, the differences will tell us which levers starlight, interior heat, cloud height, ocean depth matter most. Either way, the cosmos stops being abstract and becomes comparative physiology at planetary scale. There is a human reason to care that has nothing to do with aliens waving back. Discovering life elsewhere would not shrink Earth. It would enlarge responsibility. It would prove that chemistry tends toward company when given time and shelter. It would make resilience our native story rather than a fragile exception. It would say that the silence we feared was only in our instruments, not in the universe. So here is the sentence this era is training us to say without drama and without doubt. A distant atmosphere refuses chemical equilibrium in ways most simply explained by continuous replenishment, compatible with liquid water, persistent across methods, wavelengths, and time. When those words are true here or on the next world, they will not require exclamation points. They will be heavy enough on their own. Until then, the work is ordinary and heroic. Point a telescope, measure a dip, subtract the star's moods, argue about the noise, publish the recipe, predict a line, and check it. Predict a glow and check it. Predict a phase curve and check it. Repeat until the fragile parts fail and the sturdy parts remain. That is how a whisper becomes a statement. That is how a claim becomes a fact. Look back, one last time, at the picture that started this story. A planet 2.5 times Earth's radius. A hydrogen veil. A deep, dark sea. Dim light from a small red sun. If life is there, it is not grand. It is persistent. It is the patience of cells dividing in the dark and exhaling molecules that drift upward, carve narrow absences in starlight, and cross 120 light-years to land on a mirror we built together. Those absences are the footprints. We follow them because they are the simplest proof a planet can leave. If K218b is not the place, another will be. If this number is not the verdict, another pattern will be. What matters is that we have learned how to read the sky for the work of life. We are no longer waiting for a radio hello or a silver ship. We are watching chemistry refuse to sit still. We are listening to the universe the way a physician listens to a pulse, gently, repeatedly, with respect for what the body might be trying to say. When the pulse is clear, we will know, and the night will be the same as it was the day before, stars scattered over quiet rooftops, yet we will stand under it changed. We will let the dark feel inhabited. We will hear a conversation older than us, wider than us, and still just beginning. That is what Webb has given us already. Whether or not this one world crosses the line from maybe to yes, the ability to trade wonder for evidence, and evidence for understanding, without losing the wonder at all.